at the end of summertime, there is very little light available. There is very low light. Welcome to the epic online meeting on low light cameras. On Monday, 25 of October, the epic online technology meeting is on low light cameras. For most photonic technologies, there are two application fields, consumer and niche applications. Let's put some light on the subject. So, number one, consumer. We have the professional Hollywood cinema look, which is becoming available on high-end mobile phones. But these beautiful reflex cameras with their heavy glass lenses and full-frame sensors have an advantage when it comes to shooting in low light conditions. Ironically, although Apple's new iPhone 13 Pro is claiming it may one day compete with the larger optics from Red, Sony, Nikon and Canon, they are using camera technology from others. So in our meeting on October 25th, with companies like ST Microelectronics or Leica in the room, we will be asking ourselves what are the key elements in manufacturing future-proof sensors. What kind of optics are needed for accelerating the focus in low light conditions? And what is the state-of-the-art and unmet needs in shutters these days? Remember the days when the only way to take a picture of the northern lights was by leaving the shutter open for 45 minutes? Today's time-lapse photography has changed all that. I wonder what role automation plays in capturing those few photons for the CMOS sensor. And number two, the so-called niche applications, from medical to real-time process monitoring. In a world of fully automated production lines, why waste money and electricity by lighting the factory floor? What if production process can operate in extremely low light conditions, but that requires monitoring sensors that can operate reliably with just a few photons? Another dark application, of course, is helping surgeons operate inside the human body, which doesn't have its own internal lighting. And how about microscopy? Did you see the S-pads used by Horiba? Oh my god, I love S-pads. And maybe the big one, automotive safety. We welcome Tier 1 suppliers Valeo and Ibeo in the room because we know that the future cars will use hundreds of cameras that monitor what is happening all around the car. Is there an advantage in using low light cameras over LiDAR? Let's make a match between the automotive needs and the sensors of First Sensor or Caleste. But you know what makes me excited the most is that consumer and niche applications are colliding. A recent epic success story is a collaboration between Prophecy and Sony around the volume production of event sensors. These detect motion, not images, with ultra-high efficiency and resolution. So let's explore the emerging business opportunities coming out from the shadows. See you on October 25th at exactly 3 p.m. It is our last meeting on summertime. It is our last meeting on summertime. It is also 3 o'clock and 4 minutes, and now it is time to start the meeting. First of all, I would like to say thank you to the epic team that is behind me today. Neringa Norbutaiti, event manager, making sure the logistics are going smoothly. Elena Beletkaia, who worked like crazy on having the key companies in the sector, like Valeo, everyone. Antonio Raspa, innovation manager. Tracy Vanik, who is the head of market research, and myself, who is just having fun with you as a community. Today, I want to celebrate that we have reached number 750 epic member. We keep growing thanks to you, but it's not about how many members we have. It is not about how many members we have, it's because we know each member individually that makes us special. And on that, the technical team of Epic and the events and marketing team of Epic are doing a fantastic job. I'm speaking today on the behalf of them, and because it's Halloween, on behalf of other pumpkins that are making Epic an excellent adventure. Thank you very much, all of you. Just to remind you, organize events, provide access to the network, help you raise capital, have the biggest website to find a job in Photonics, jobsinphotonics.com, and provide you with excellent market data. today is half season already of the season 5. So far, we're getting great feedback for this season. We focus this season on trying to bring new technologies to the end user side. Pay special attention to the one next week on super continuum generation with the success story of NKT and Lucas on the potential suppliers and end users in the room. What lasers are really, really cool. And also for those of you in quantum, those of you in quantum tech, on the 3rd of November, gravitometers, those sensors that can detect any changes in gravity and can predict earthquakes or read the brain waves. It's quite a fantastic technology that if you're developing CMOS sensors, and many of you are, this could be a fantastic market. But today is all about low light cameras. I would like to first of all acknowledge the cooperation and the support of the companies without which this meeting wouldn't be possible. And those are our sponsors today. First of all, acquiring high quality images in low light environments is challenging, very challenging, especially with no compromise on speed or resolution. With that, I would like to have the company that really brings added value to that, where it's feasible on shortwave infrared first light imaging uses state-of-the-art sensors and provide high quality cameras with very high dynamic range. All the way from the Netherlands with almost 30 years experience, Avantes provide the customers with Neblik spectroscopy solutions and tailored to their application and research needs. But PI Imaging, also a great company in the camera manufacturing, they provide SPADs, very sensitive SPADs, and I love SPADs, so it in the introduction, at 100 kfps. Wow, with the time gated at 20 nanoseconds. All the way from Barcelona, we have Imasenic, which is a dynamic and experienced company providing custom CMOS image sensors. From Belgium, we have the company Caleste, who are providing, if you need a real super image sensor, you have to talk to them, you have to talk to Young. They achieve even a noise level below 0.3 noise electrons. 0.3 noise electrons. Oh my God, you're looking for black coatings. You need to talk to Akhtar, all the way from Israel. They provide advanced coatings for the maximum absorption, the real black. And all the way from Japan, but a very European company in heart, Hamamatsu is providing any kind of detector, sensor, QCL, any photonic component that you need. Talk to Hamamatsu experts. They are the right people. And talk to my expert, who is always the right person, my very, 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 very fantastic colleague, Dr. Elena Beletkaia, all the way from Amsterdam, the Netherlands. What's going to happen today?
Hello, Jose. Great to hear you again at this fantastic meeting. I think we have a very interesting agenda today. We are focusing on many different applications of low light cameras and sensors. We will have presentations from automotive, from Valeo, Ibeo. We will address also more on a camera manufacturing side and even a defense sector. But more than that, it's very interesting that we have a full supply chain of all the companies who are interested and really contributing to the development of the low light technology. We have obviously here those who are developing sensors and detectors. We also have camera manufacturers, system integrators, all the different components, whether it goes for spectroscopy or even materials or even software and augmented reality. We also have those working on optics and coatings and some end users and many more which are presented on this slide. It doesn't mean that it's the whole supply chain. It's those who registered for this event. And I cannot wait to actually start with the presentations.
This meeting is also live stream in YouTube. So all of you following in YouTube, just remember, write your questions in the chat and I will read them in the room. If you want to get in touch with any of the participants today, all you have to do is send me an email and I will make the introduction. And this, of course, also valid for the people here with me in the Zoom chat. Use the internal chat as much as possible. Talk to each other as much as possible. Connect. That's the purpose of this meeting. If after the meeting you didn't manage to talk to the person from Ibeo, Michael Kiehn, just tell me no and I will introduce you. The same thing with Derek Savage from Valeo. Tell me and I will make the introduction because this is all about starting new cooperations. So Elena, are you ready? Let's start the meeting. Time to introduce our first speaker today. We go to the most important tier 1 supplier in the automotive sector. We go to Valeo because we want to hear from the R&D director on vision systems, on what are the particular needs for the cameras of the automotive. The floor and the attention of everyone goes to Derek Savage, goes to Valeo. The floor is yours.
Thank you very much, Jose. I will share my screen.
Sharing the screen. in a very clear fashion and receive with perfect quality.
Okay, good. So first of all, to introduce myself, my name is Derek Savage. Very happy to be here today. I'm joining you today from the west coast of Ireland, beautiful region of Galway. So this is where our headquarters for vision systems in Valeo are located. So today I'd like to quickly discuss some of the applications and some of the challenges and issues relating to automotive imaging at low light. So first of all, a little bit about Valeo, just to give the background. So we are a leader in parking safety and driving automation, particularly in the area of parking. We're the market leader since 1991 in the area of ultrasonics and the different cameras. So today's presentation will be focused very much around parking cameras for automotive, which are wide-angle fisheye lens cameras, 190-degree lens cameras. We're also a leader in active safety and in automation. So how to control the vehicle with the perception, the sensing input coming in the different environmental conditions. So when we talk about automated driving and automated parking, there are different architectures emerging. However, the trend in the industry is very much towards centralized processing. So all of the sensors on the vehicle, including the cameras, will be connected directly into a central processing unit. This is the way the industry is going. So a number of years ago, vehicles were full of these electronic control units, and they would be basically processing the input from the different sensors. So there may be up to 100 ECUs on the vehicle. Now we will have centralized computing systems in the co-located in the vehicle. So today we're going to talk about near field vision, which is fisheye cameras. As I mentioned, these are for the typical surround view cameras. Far field, which is narrow field of view. So this would be traditionally the front cameras in the vehicle that sit behind the windscreen looking forward, 30 to 70 degree field of view lenses. And also in-cabin sensing, which is a new application and very, very focused around autonomous driving. Whereby obviously the driver of the vehicle must be monitored in terms of to ensure that they're not falling asleep, they're not distracted too much, so that if you're in a level 3 system, for example, and you need to hand back to the driver, that you can actually understand what the driver is doing and if they are paying attention to the actual scene going on around the car and the driving. So they're the main applications. So automotive imaging is quite unique, I think, especially compared to consumer, because there are many drivers. And on this slide, there are the many different use cases that we have for cameras on a vehicle. So in the main use case that's emerging is a surround cocoon. So this is to be able to visualize fully around 360 degrees around the vehicle. And also now more and more towards image processing, computer vision, so detection, perception, fully around the vehicle. So within that surround cocoon, there are different applications. So we have viewing applications whereby we must show the images, show the video to the driver, and that's typically in a parking scenario. So for low light, for example, it's very important that we can see whatever obstacles are could be in danger of being hit by the vehicle. Could be children, bobby cars, smaller objects around the vehicle in the dark. So very, very important that we have that low light performance so that we're able to show the full environment to the driver as they're doing their parking maneuvers. When you move to more automation, as we all know the industry is moving towards, this becomes very, very critical because it can be very dangerous in a low light scenario with children in the family home zone, for example, where the car may be parking. So a lot of safety applications around the low light performance. And then at high speed, it becomes even more critical because as the vehicle is moving faster, then obviously it's more dangerous to the surroundings. So what are the considerations for the automotive imaging? So screen size and resolution. So this drives the actual resolution of the imager. I'll talk a bit about that in the next slide. There are video consumers, so we need image quality. We need high performance image quality for the consumers. So this could be transmitting the video from via a telematics unit to the cloud, so where it can be used by offline consumers. We have considerations around packaging and styling, which is critical for the automotive. You can't put this huge camera onto the car to make it look bad. We have performance of actual perception and detection algorithms. And around this, we have obviously the low light performance of the pixel itself and the optical path. So the imager plus the lens is critical in all of this. We also have to think about cost and the critical safety and environmental standards that we have to meet in the automotive industry. So just an example of a low light scene with our fisheye cameras. So this is lane detection. And as you can see at low light, even with the best imagers that we have, if you look at the picture in the bottom of the image, you know, the detection performance is much algorithm, it's much more challenging for them. So our job is to get the most information to the computer vision algorithms to allow them to detect the critical objects and lines and vehicles that are around the vehicle in the low light scenario. So just the last slide, just speak a little bit about what has happened in the automotive industry, how it has advanced since around 2010. So in the early days, we had VGA sensors. We had very large 6-micron pixels with no HDR, a 60 to 70 dB dynamic range. So there's been numerous advancements that have brought us to where we are today, particularly around backside illumination, which was a huge increase in terms of the low light performance. The dual conversion game that came in around 2015, 2016. LED flicker mitigation, which is a major issue for automotive because of the LED lights that are now very common in the automotive world. So if you have to detect the lights of oncoming vehicles, you need to ensure you have this LED flicker mitigation. And then we have the changes in the color filter arrays. So primarily, you can see that the resolution has increased significantly. 1 megapixel now, standard would be 8 megapixel for detection performance. And this brings its own challenges in terms of pixel size. So all in all, we have a lot of challenges, a lot of different applications in automotive. And we are looking for the optimum, the best image quality that we can get at low light for these various applications. Thank you.
Okay, thank you very much for this great introduction. And now we also got slight introduction directly into what are the needs for automotive industry. But since we are in the EPIC meeting, let's also start the first Q&A with our favorite EPIC question. So if you sum up it just in a few phrases, answering what you can do for them and what they can do for you. So what you can do with the members and what you're looking to get from them.
Yeah, so typically we have in the automotive world, we've brought a lot of advancements in the image sensors that have come from the consumer electronics, but actually the constraints and the applications are much more challenging from an automotive perspective. What we're looking for is cost-effective technology solutions, particularly at the pixel level, but also maybe at the post-processing level to allow us to recover the information if it's lost or if it's reduced at low light. So we're looking for any technologies that can help us understanding the world around the vehicle at low light, if it's post-processing software or if it's at a pixel level or a combination of both. That's pretty much what we're looking for today.
Okay, sounds fantastic. We obviously gonna have plenty of questions to you and even more introduction afterwards. But let's start with a question from Eric from ST Microelectronics, one of the biggest producers of low light sensors. Eric, please unmute yourself and let us know what's on your mind.
Yes, thank you for your kind words and the presentation from Valeo. As usual, in every, let's say, automotive presentation, we see images with cars under the beautiful and sunny Californian-like weather. do you have any particular metrics to measure the performances of your sensors under rain or under snow, under adverse conditions?
Yes, so that is one of the major challenges that we have. So exactly as you said, these lovely videos with no rain, no snow. So typically what we see is that low light is a critical factor always. However, if you add in snow, if you add in very harsh environmental conditions, even if we're talking about high temperature or very low temperatures, then the image quality and the noise gets worse, the noise levels go up and the perception algorithms degrade. This is a key point because one of the drives in the industry towards level 4 automation is for 24/7 automation. If you have a robotaxi, you need to be able to work in all environments. So this includes all weather environments. So we have a lot of data, but we see that it degrades significantly in those adverse weather conditions.
Okay, thank you. We also have obviously many more people who are developing different sensors. So, and we have questions from them. And next question comes from Renato from Imasenic. Renato, tell us a few words about Imasenic and what is your question to Derek?
Okay, yeah, thanks. So yeah, we develop custom image sensors, low noise, so for low light level, high speed, and also we develop SPADs. And in your last slide, you didn't mention SPADs, single photon avalanche detectors. Any reason? Because nowadays SPADs can be, you can do imaging arrays with SPADs, and I know they are developed also for automotive application, although it's maybe more for LiDAR than for imaging. But maybe you can comment on that.
Yeah, maybe that's something that we could follow up on. I think Renato. I think that mainly it's cost driven, but if you have some other information, it would be very interesting. That's the cost of, just for example, the cost of a typical automotive camera is something between $20 and $40. So you really are squeezing out in terms of cost, and that is one of the main constraints that we have. But if you have some information that's relevant, we'd be very, very interested to discuss with you.
Okay, thanks.
Fantastic. I know one person in this room who always has a lot of relevant information and even more questions. And as you all guess, I'm talking about Jose. Jose, what are you thinking about?
I'm thinking about, first of all, I'm thinking about Derek when I had exactly the same concern as Renato. There were no SPADs mentioned in the presentation, and that freaked me out a little bit because I think it's the next big thing when it comes to the automotive industry. But one question that for me comes to mind is that we have been having many meetings with Valeo, Ibeo, and other automotive companies about LiDAR, and today we are talking about cameras. And everybody knows a bit of what Mr. Musk is saying about the LiDAR for automotive. I would like for you to tell us a bit of your vision. Do you think we are going to have low light cameras replacing LiDAR because of cost issues, or you think that there is place for both? And don't be politically correct, because I know Valeo LiDAR makes LiDAR too. Let's tell me your honest opinion, please.
Yeah. So Mr. Musk has lots of interesting views on this. I would say in our experience, multiple sensors will be required to reach the high levels of automation. So cameras alone, I don't believe will be enough. I think you will need radar, you will need LiDAR. There is a requirement for other sensors as well to reach the redundancy and reach the automation levels that we need to get to level 4 or level 5.
I do believe here that we are, the industry, especially in the automotive sector, we are having a bit of problems understanding what is low light cameras and what is night vision. Is there that doubt, in your opinion, in your mind? People understand what is what, or is there some need for clarifying these technologies?
Yeah, so night vision obviously we're talking about a different wavelength. Everybody knows that. Where we come from in our industry is, I mentioned the viewing aspect. So we are still expected to deliver viewing video to the driver also, and on the same cameras do the perception. So purely for perception is not acceptable for our cameras. Now, in the future of full high-level automation, there probably is room on the vehicle for more and more different types of cameras, thermal cameras, infrared, etc. But right now, we are being asked by the OEMs to produce cameras that can be viewed and also have the computer vision perception done in parallel.
I have in the room a very good friend that I want you to meet, Jan Vermeeren, all the way from Belgium, from Caleste. Jan, good afternoon. What's on your mind?
Hi, Jose. Yeah, I have a question for Derek. You consider now at this moment still, I guess, visible cameras and purely passive. At a certain moment, you could also consider to go to, for example, the near and active illumination. You don't at that moment disturb, let's say, the other participants to the traffic, and you can, let's say, tailor your light like you want.
Yeah, so you're talking about active illumination, is it?
Active illumination and in the near infrared instead of using pure passive, let's say, color visible.
Yeah, exactly. And we do have some research going on in that area, and it is certainly, obviously, Valeo, you may be aware, is also a very successful lighting supplier as well in the automotive industry. So that is something that we are very much actively investigating is active illumination and the combination of the different illumination types with different imagers. Yeah, so it's absolutely on our mind. Thank you.
I have another question coming from ST Microelectronics. Before I give him the floor, Derek, this you saw in the introduction, we are seeing motion sensors, event sensors are being promoted also for the automotive industry. Are you familiar with those, with the need to not collect all the full images, but only detect things that are moving?
Yeah, I mean, it is about, in the end, it is about as well the processing capabilities on the vehicle. So I certainly believe there is a future here. It's a technology that can be used. As you're probably aware, I mentioned the central compute systems and centralized computing on the vehicle. It's still very difficult to process these very high resolution cameras. So if they're 8 megapixel or 12, we supply up to 20 megapixel cameras. So you could have 8 20 megapixel cameras on the same vehicle. So processing these every pixel in these cameras is probably not realistic, 24/7. So absolutely, event-driven sensing is certainly something that could be a very good solution for this problem.
So for me, one of the big challenges that you have is how much data you have to process real time. And I think there is the magic trick. I want you to also meet, you already talked to him, but I want you to meet again our key person at the key company in semiconductor manufacturing in Europe, ST Microelectronics, Eric Masarerat. What's in your mind?
Yes, thanks, Jose. I wanted to ask another question, maybe more directly to Derek regarding adverse imaging. Do you consider shortwave infrared as a solution to, let's say, improve your performances under rain, under whatever kind of?
Yes, absolutely. And that's something we're investigating. I mean, in terms of the IR spectrum, we have done a lot of experimentation around, how much light we can let in that will not affect the image quality in terms of visualization. What we see now with the advent of these camera cocoons, that where you're not showing the image to the customer, that IR will certainly play a big factor. Yeah, absolutely.
Do you have any idea of when you will be able to introduce it on the market?
We don't have any series with any of the OEMs. I don't believe there's any intent to have a series production in the next couple of years. It's probably in the, I would say, 3 to 5 year horizon.
Okay. Thanks.
Derek, for me, it is fantastic that you're here as head of R&D for Valeo. You already said the kind of things that you would like to collaborate with, but before I let you go for a bit and we meet the person from Ibeo, I want to go back to this slide that you show us. I noticed that the slide goes until 2022, more or less, 2023. If we had this meeting again in 5 years, let's say 2026, what kind of things do you think you would tell us differently? What kind of thing you see a little bit beyond the horizon? Of course, please tell us what you can tell us and don't tell us what you can't.
Okay. So I would say the key point of the slide is to show that the trade-off and the difficulties, the challenges between pixel size, low light performance, high dynamic range, and flicker mitigation. And this is where with the evolution up until now, we see that we are reaching probably a plateau or the bottom in terms of the actual pixel performance in terms of the quantum efficiency. We don't see huge gains there. So if we look into the future, I would see that the standard cameras would move from 8 megapixels probably to potentially 16 or 20 megapixels. And the challenge then is how to at least retain or improve the low light performance with that smaller pixel size. And how do we ensure that we can get the same noise levels, we can get the same image quality, as I mentioned, with those higher resolution imagers. And this is one of the main challenges I think that is there in the industry for the next few years.
You know what I want you to tell me, but you're not going to tell me. You're looking about high dynamic range and price reduction. So I think graphene cameras could be something to be considered seriously. Yes? Graphene-based cameras. If we talk about high dynamic range and we talk about lower price. Leave it in the back of your mind. I want to revisit that later, but this is some thought I think is coming, but I don't know how fast or how early. It is time now to move to the next speaker today. We started with Valeo. We couldn't have started any stronger. Derek, thank you so much. And we go now to one key tier one supplier in this industry who has worked very closely with Epic on bringing new technologies to the LiDAR marketing automotive. The Senior Vice President of Advanced Engineering of Ibeo is Michael Kiehn. Michael, thank you very much for being with us this afternoon. It is great to have you in the room. Tell us how the 750 Epic members can help Ibeo being even greater than already is. The floor is yours.
Thank you, Jose, for introducing me. So, yes, I will take the chance to address or drop some of our problems we have today to the audience and hoping for some solutions to get there. First, I have to ask, is it okay with my presentation today because I can't see? So you see the slides on the screen?
Yes,
okay,
we do.
Great.
But please go slideshow mode so we can see them even bigger.
Oh, I try to.
Yes.
And now it's wrong. So,
perfect.
So you see the right slides?
Yes, fantastic.
Okay. So actually today I would like to talk first. I would present one of the most challenging use cases for LiDAR, coming then to solutions, how the LiDAR industry is going to tackle these. And this directly also raises some open questions or points to improve to the audience where they actually can benefit or can participate or even contribute to our solution. And then finally, I would conclude with some kind of a system view, how the LiDAR system on a complete vehicle might look like in the future. So, but before I come to that, maybe just a few words about myself. So I'm Michael Kiehn. I'm Vice President of Advanced Engineering at Ibeo, and I'm working on LiDAR for more than 20 years now. And at Ibeo, actually, for a similar time, again, more than 20 years, we're working on LiDAR for automotive applications. I have one product in series which actually helped Valeo to bring into mass production, and now we are currently working on our first generation of solid-state LiDAR. So this is one of the scenarios that we probably see addressed by autonomous driving rather soon. This is a motorway, and as you see in a first glance, this is probably not what you would imagine when thinking about low light, because in LiDAR it's a bit different. We can have low light even at daylight conditions, and real low light conditions at night are even better for us than this, because at night there is no noise or less noise then. Now what we see here is a traffic scenario where it's rather easy to do this driving. More challenging is actually this one, this scenario. And you see why, what's going on here? Well, what we see here, first of all, there are no other participants in the traffic. So meaning, first of all, the customer, the driver, would not understand why in this scenario you would go slower than in this scenario we've seen on the left side. But there is actually a reason for why you have to do this today. Because in this scenario, with an actually empty road, you need to be able to detect real small obstacles. So in this scenario, it could be that there's a tire or whatever has been left on the road in some distance, and here you need to avoid this target. Unless the other case where you see many other vehicles, road traffic participants are already reacting to this say obstacle on the road. Here you're the only person, you're the only sensor that can see that. So we actually need to be able to detect the small obstacles on the road that you have to avoid, and you need to see this at a rather large distance. So one typical obstacle mentioned by many customers is this tire left on the road. It is rather small and it's very less reflective. So you need to be able to detect this. And when you look at this tire, I've said already, it's rather small, so it's not only about getting low reflection back, it's also getting low reflection back at a very high resolution, because also you need to be able to determine whether it's as small that you can drive over it, or that it's as high that you have to avoid it. And this is something, the difference between 10 and 15 or 20 centimeters. And from this, you can do very easy math and come up with a resolution that ends up for a range of 200 meters that you probably need to have for this obstacle, where you come up with a resolution of 0.03 degree. So what do we need to have? Summarizing this slide, actually, we need to have sensitive detection, I would say detectors, but detection, and we need to have a high resolution to be able actually to spot these small obstacles on the road. So what is LiDAR industry doing at the moment to cope with this challenge? So the first one is not actually low light, it's just putting more light to the scene. And to be able to do that, as there's still some eye safety restrictions to lasers, you have to shift the wavelength. So many systems, I would say even most systems today, work in near infrared, but there are definitely the eye safety limits are much stricter than in the, I should say, shortwave infrared in this place. So we need to shift to shortwave infrared, 1550, something like that. This is basically to be allowed or to be able to have a higher output power, to put more light to the scene without harming people out there. Well, still detection technology there is not silicon, so it's more costly than actually silicon detectors. So for sure, what is needed there is a still low cost detection solution. Another issue with the detectors are there, they are still quite noisy. Whether it's talking about S-bands, you've got to consider dark count rate, or talking about linear mode detection, it's dark count that you actually need to consider there. And another point is probably not for the audience today, but laser sources are also some not completely solved topic yet, because thinking about laser diodes as it's used in automotive LiDAR for the most of the time, in near infrared, say shortwave infrared laser diodes can basically do the same with respect to power output and brightness. But if you want to have more output power, these diodes neither can do. So actually we talk about lasers that are more solid state laser, fiber lasers or whatever, and therefore sure cost is definitely a point that needs to be addressed. So another approach is, well, okay, have a higher sensitivity on the receiver side, single photon detection. This is actually something that we do at Ibeo. So we have a system based on a 2D S-band array and a matching 2D VCSEL illumination unit. What we would need from that. So today we started development on that in 2014, 15. And there, what we have in our system today is a detection probability of 4% at around 900 nanometers. So definitely high detection probability is something beneficial. So we're thinking about something finally should be between 20 and 30% at wavelength 900 plus, ideally 900, 1400 meters. It doesn't need to be more, because if you see, we're working also in daylight. We've got background detections as well, and as long as we don't have a big improvement in dead time on these S-bands, It's not beneficial to go beyond this 20 to 30% because then you're blocked most of the time by background detections. So currently our sweet spot we find from our detection, from our calculations is somewhere between 20 and 30%. Today we're already working on detectors that are going towards, say, 15%. So there's still some room, and for sure room is as well with respect to the dead time of these pixels. So going to something, today we're around 10 nanoseconds, going to something that's significantly less than that. For sure, similar to the first approach, higher peak power on addressable VCSEL arrays is something that we would really appreciate in this field as well. So coming to something, say, rather different now, for sure, when you talk about low light detection in an active system, you can also consider coherent detection. So that's something that is out there now for some years, also in the discussion for LiDAR, and big advance has been made there. So basically, we'll talk there about FMCW modulation of the laser, so FMCW LiDAR. But there, if you look at the patent applications coming up, there's also other means of coherent detection. So for sure, if you talk about FMCW, what is needed there is a tunable laser source that also has to be coherent, provide a certain coherent length, meaning certain coherent lengths. So it needs to be at least twice the round trip time your light has. And if you think about measurement range of, say, 300 meters, then the round trip time would be 2 microseconds. So coherence length needs to be more than 4 microseconds for these lasers to do this chirp up and down for FMCW. So this is something that needs to come at a, say, affordable price. And then what we need, again, also is, say, highly integrated silicon photonic circuits to do the demodulation and the coherent detection of these signals. There's one point that actually comes with this. Would probably at some point in time to address the market really very good. You need to multiply the system because thinking about a, say, one channel measurement, which is something you probably would do first, and then you have to do a 2D scan. And thinking about the available time budget that you have for your scan, and considering a certain angular resolution I already mentioned, 0.03 degree, as well as a certain field of view, then you can do a fairly easy calculation and find out that this does not match to your frame rate requirements. So you're actually simply not able taking this measurements within the desired time frame. So meaning you have to do things in parallel, and then it actually at the point where it becomes very costly. So this is where we need to think about split the laser and have cheaper lasers, as well as have multiple channels on the receiving side. So I think at this point already, I mentioned many points for the industry that where you could dig in and provide some solutions, potential solutions, technology that will help to overcome the limits we have there today. And just to, if you're not sure where you should focus on, whether high peak power, single photo detection or coherent detection, I would like to have a glance on at least our idea about a system, a LiDAR system at the car would look like in the future. So basically that means you don't really have to decide. Looking at this, say 360-degree coverage. So coming from a normal passenger car, it's not a single sensor doing this, because the single sensor that would be able to see 360 degree would be mounted on the roof of a car. This is where at least the traditional car manufacturers don't like to see anything like this laser LiDAR on top there. So you will split the fields of view around the car. And then actually there's another point. You don't need full performance into each direction. So what I mentioned, this use case at the beginning, this tire on the road, yeah, for sure, this is something relevant use case just in front of the vehicle. So meaning you only need a certain field of view, say as example 32 degree, you really need this high resolution and high range. So for this, for sure, we need something like, or can consider something like a coherent detection or shortwave infrared. For the other areas, we need a large range, reduced, where I don't need the large range, and also reduced resolution, angular resolution, but wider field of view. You go to different directions, different technologies like this VCSEL S-band array approach, which is much more cost efficient. So meaning there is room for different applications in future, and I think not only room, there's also the need for different technologies in LiDAR to address the full sensor suite that is actually needed for autonomous driving level 4 or 5 in the future. So I think now it's time for your questions.
Thank you very much, Michael. There are obviously a lot of challenges still within the LiDAR technology and low light detection. And it was quite interesting for me to see, and as you mentioned, that when there is no traffic, it's actually more difficult to orient yourself. And it took really a moment to understand why. I mean, there is nothing, usually you prefer it that way, then you can top the gas and just follow. However, let's address the challenges that you were bringing up. And since you were talking quite a bit about single photon detection, we have quite a few companies in the room who are working on these technologies. So I would be very curious to hear from them. So if you don't mind, Renato, shall we maybe start from you to hear how Emosenic could fit into the solution? Do you think that there is some room for cooperation between you and, yeah, maybe there is something we can work out today?
Yeah, very good question. Thanks, Elena. Yeah, I think there could be room for cooperation. I mean, maybe we should have a chat separately offline, but yeah, we also work on similar solutions, so that could be very interesting to have a chat outside this room. But I have a question as well for you. So you mentioned the higher pixel density in the previous slide. Can you be more quantitative on this?
Yes, I definitely can. So actually what we have today going into production rather soon is an array, which is what I call rather coarse. It's 100 by 128, what we call macropixels. So each detection pixel is still formed out of 10 plus single detectors. This is what we have today. We are already working on a generation aiming for a start of production 25 that then comes from this about 12K we have there to a resolution of say 160K pixels. And say the goal for a generation starting from 28, this is where we are currently working in advanced engineering at Ibeo. The aim there would be to go something between 300 and 600 pixel resolution there. It's not covering the full field of view you see here. It's just the number of pixels required for such a single unit you see on the slide here, like say the 120 or 62 degree unit there. So going to at max 600K pixels that we need to have there, for sure, at a reasonable size, because area costs.
Okay.
Okay, thank you. So coming up next, we go to other very probable cooperation that you should consider. And I'm very glad to see that Jan also has a question. Jan Vermeer from KLST. And I think you still need to unmute yourself so that we can hear your ideas and questions.
Okay, no problem. Thank you very much.
No, it's better.
I want to be a little bit provocative. In one of the previous slides, you mentioned go to single photon detection. On the other hand, let's say what you want to have at a certain moment is say decent signal to noise ratio.
Yes.
Before you're there, you need to have, let's say, at least a few hundred to a few thousand events detected. But at that moment, you're far away from a single photon detector. you can do it as good, so to speak, with a normal integrated detector.
Yeah, so that's actually, we're already using SBETs, and yeah, you're right, it's probably not really about single photon detection, it's time correlated single photon counting that we do. So you're building histograms, and for that we need a few hundred cycles before we come up with the say signal. Still, even though it's from the final result and comparable to a linear mode detection, still there's a good reason for doing so, because if you want to have this number of channels as we have already today, some 10K, there's no way to have this in an integrated way with linear mode detection at a certain sensitivity. So if you think about say normal photodiodes, for sure you could do this, but still to get to a sensitivity level that we need, it's still an APD, it's linear mode APD. And for sure what we need is for each channel, or at least for a certain number of channels, to have the analog signal conditioning, transimpedance amplifiers. And having a bunch of 128 or even more transimpedance amplifiers integrated in single silicon is a very hot topic. It's not easy. So this is why we came up with this SBET approach, where we actually can integrate very easy in a CMOS process, and you can do the calculation, the histogram, and all the thing again already on chip, which is a huge benefit cost-wise. Even though technically this might not be the ideal approach.
Okay, thank you. Jan, do you have something more to comment? But then you will need to unmute yourself again.
Yeah.
No problem to unmute. Yeah, luckily I do that mainly to avoid that I'm disturbing too much. If you want to do, yeah, but if you want to do coherent detection, let's say, how do you really execute that? Because you state, let's say, very much at an, let's say, conceptual, descriptive level. You did not enter into, yeah, the way how you realize, or should we take the discussion offline?
Yeah, so actually we can have a discussion offline, but anyway, the way we are following by Ibeo is this time-correlated single photon counting approach. We are currently not working on FMCW or on coherent detection. This is still something that is in the market, and we see this, and we see this also at some kind of competitive challenge. And we might consider having a look into this as well, and would appreciate some help from the scene to get to the silicon photonics there. But still, what we're currently following at Ibeo is not this coherent detection. Okay. So this is why I was not very excessive on this.
Thank you for all the replies, but for sure you should continue your conversation offline, same as many others. And Jan, thanks a lot for being just a little bit provocative. As you all know, we have one person in the room who really loves all the provocations in here. Jose, what do you want to bring in now?
I would never provoke anyone. No, that's not me, please, Elena. No, we are a group of friends here who love working together. I have Michael. So there is I don't believe we can have both FMCW or time of flight or visible based. What do you think technology is going to win for automotive? Or you think we are going to have different types of LiDAR in the car? I don't think so.
I'm convinced we will have different types of LiDAR in the car.
So the only reason to have FMCW, for me, I believe, is that we have problems with eye safety and with interference with other cars. So that's why we want to have the coherent detection. If we invest on having silicon photonics in the car, what would be the problem to solve for the 800 or 900 nanometer wavelength?
Yes, still with this FMCW approach, from a single unit, you would not be able to cover the full field of view. So you need this definite FMCW definitely to get this high performance towards the front, and maybe at some point also to the rear. If you want to actually avoid obstacles, then you have to have a, say, wide look in the rear as well. But still, this technology seems to be rather expensive, I think. And so, having said, you cannot do this with a single unit. And then there is probably no point to have several of these units having a performance that you actually don't need for views to the side. Because to the side, you don't need to have this large range. So we'll see different technology there that is rather designed to have a say, mid-range or short range with a corresponding dense pixel density that covers that area there. So I'm convinced that we will have all types of, not all types, but at least 2 types of sensors in the camera.
All right, so well, it doesn't matter because at the end of the day, I believe that only time will tell. Michael, one thing that I want you to do is to meet an important EPIC member all the way from Neuchâtel, a company that is developing single photon counters, because we want to understand how the single photon counting cameras could have a role in automotive. PI imaging is in the room. Michelle, all the way from Neuchâtel. Good afternoon.
Hello, good afternoon. Nice
you have a question in mind, but first I would like you to tell us what is PI imaging, because I believe it's really your first EPIC meeting in which you come as an EPIC member.
Actually, I also already participated in the microscopy meeting as well. So that's the second one. I'm glad to pile it up. At PI imaging, we develop SPAD arrays, which are, I think everyone knows in this room, and they are very good for time correlated single photon counting. Low light imaging. We're specifically focusing on high speed and low light imaging. As you know, SPAD cameras, they do not have any readout noise. So we think that with gated operation and high speed imaging, that's a good niche to attack. Specifically for Michael, I had a question about the how do you plan to pipeline all the data of such a big array that you plan for 2028? And I assume that you're also considering some coincidence or also gated operation methods that have been proposed in recent few years
so,
in research.
Yeah, thank you for raising this topic. Actually, dealing with the amount of data is definitely another point that's, say, away from photonics, but still a very important point to solve. So, and this definitely starts immediately, say, at the front end, after you did the timing measurement. And we're currently also looking in say, compression immediately after the timing measurement. So I can't talk too much about it, but there are ways to come up with a very, say, data efficient approach to get to kind of a histogram, just using a different description of the histogram there.
Okay.
This is something we follow on there.
Are you designing the cameras by yourself, the sensors by yourself, or you're outsourcing that?
No, we're not designing it by ourselves. So we had for our first sensor a cooperation with a, say, semiconductor manufacturer that is very good in SPADs, and we say kind of co-design. So for sure, the SPAD architecture is not ours.
Yeah, but from the system level.
Yeah, but we definitely defined how we would like to have arranged the SPADs and what kind of processing needs to go in there.
Okay, cool.
What it has to do.
Michelle, when I look at your camera, you say that it's the size of a credit card. I would like to handle it, but what I would like to ask you and to ask Michelle and also Derek afterwards is, did you design this camera with the automotive market in mind? And if not, what is the applicability of this camera for the automotive market? We are talking about these 23 hexagonally packed single photon SPADs.
Yes, this is our first commercial product, but we also have in the pipeline, actually to be released this month or the next month, a 1/4 of a megapixel SPAD camera, which has the property of being able to image 100 kiloframes per second without readout noise. And as you can see from the website, we have very good photon detection efficiency and very low noise. We try to aim at the niche application of oversampling and gated imaging, specifically not for these bigger cameras, not for a single photon correlated detection. Yeah.
So Michelle, and then I would like to come to Derek. Michael, what do you think the aspect ratio, the size, the way that is packaged? This is the current camera. Of course, a 250 pixel one is coming in a couple of months. But is this something automotive format? Do you see this possibly tested at Ibeo?
So actually, it's hard to spot the dimension from this. We said it's basically credit card size. So this is what today our transceiver, meaning emitter and receiver, is. So there's probably still some room for size reduction, because we just recently learned again size matters.
Yeah, of course. I mean, this is the whole system. The chip itself is typically from 1 by 1 millimeter to 10 by 10 millimeters. Yeah. And this is then, I think, in the range that is appropriate for both automotive and other applications. Maybe not for consumer, but automotive, I think, is fine.
Yeah, for sure. So actually, size matters, and yeah, maybe it's going already into the direction. What is not shown here? For sure, you need some optics in front of that as well, and then you need also some illumination. Then, and it immediately gets a bit bigger. So,
of course.
Yeah. So, size currently in the market is still a challenge.
Yeah. Just to mention, considering the specifications, so the process of fabrication itself of the chip is certified.
Yeah. So you're probably working fabless, aren't you?
Yes, that's right.
Derek from Valeo, we said already size matters and a lot. We also talk about price, and I know there are concerns about using SPAS for price, although I don't agree with those concerns, but I know there are concerns. What is the first thing that comes to mind when you see a camera like this, which is only the first generation, second generation, 250 pixels coming in 2 months? What is the first thing that comes to mind, Derek?
Yeah, so currently the cameras that we would see that would are I suppose meet the styling requirements for the OEMs, particularly if we're talking about typical consumer privately owned vehicles. It would be something like between 17 and 20 millimeters diameter on the lens. So we're talking about that size, and then this is like a little eye that can be hidden in the vehicle. Something like this is obviously much more difficult when you're talking about multiple cameras around the vehicle. But when you move to higher levels of automation, and for applications like robo-taxis, for example, where styling may not be so critical, then maybe it could work.
I love asking, so prefer not to answer if you don't want to, but would it be possible to test this camera at Valeo or Ibeo? I would be happy to go to Neuchâtel, pick up the camera and Michel in my car and then drive.
Yes.
Is it possible? Is there a way for an experiment to test the camera in some conditions?
Of course. Just to mention again, it's a gated camera, SPAD camera, which has a very high frame rate. So it's not correlated. It does not output timestamps. But still, I think this. I guess in Valeo you also have issues with the frame rate. Of course, you want to have a highest frame rate, and there are many techniques popping up today. One of them is quantum burst photography, which oversamples the image scene to create also a higher resolution image finally. Higher resolution than what you have in the camera itself. So I'd be happy to test it out and see if specifically this high speed can benefit automotive applications as well.
If you ever want to have a chat coffee or quantum burst photography, I would love to join. That's a really fantastic topic as well. Yeah. But we started talking about SPADs. We have Caleste in the room, we have Imasenic in the room, we have PI Imaging in the room, and we also have one of the market leaders in the room. We have the company Hamamatsu. Sebastian Beer, many times I already told I love your surname, but I also love the technology that Hamamatsu has. Could you share with us one slide? Because I would like to ask, based on the experts of Hamamatsu, a follow-up question. I think you have some slide to share with us.
Yes, I do have exactly one slide. Give me a second, which goes in a probably quite different direction than all the stuff we've been talking about now. It'll be more of the niche applications you told us at the beginning about, Jose. So actually, Hamamatsu is probably most known for its photomultiplier tubes. However, the first Hamamatsu camera was developed the same time around 1953, long time before I was born. However, we've been delving pretty deep into the low light issue or sensitivity issue. So the first single photon counting camera came around somewhere in the 80s, at that time somehow based on image intensifiers. And there were actually two routes taken by us. On the one hand side, the electron multiplication similar to, well, image intensifiers or EMCCDs or EBCCDs. And on the other side, on the low noise cameras, CCDs, and nowadays mostly CMOS. And just this year I think that was in May or June, we released the latest camera, which actually also has a readout noise of less than 0.3 electrons, which makes it possible to not only count single photons, but really count photons, so count photon numbers, of course, at the cost of speed, because the bandwidth limitation kind of persists. But with this camera, we're able to discriminate between 0, 1, 2, 3, up to 200 photoelectrons, and all of that at a peak quantum efficiency of 90%, meaning with this camera, actually the sensitivity issue under certain assumptions is more or less maxed out. So that is pretty nice. What we're looking for there is now specific applications needing those unique combination of features. Because obviously we've had some success here in very niche applications, just like quantum applications, and who are obviously interested in discriminating whether they detected 1 or 2 photons at the same time. And other general researchers really like that camera for its sensitivity part, but that photon number resolving feature of that camera has not been used to its fullest extent. But in the end, it's just like a technology that has been available for half a year or something like that.
When you talk about niche applications, because I saw your demonstrator 2 weeks ago in Glasgow at the Photonics conference, so I was quite fascinated by the Orca. But when you talk about applications, microscopy is the big thing. In vivo tissue monitoring is also perhaps something that is growing quite fast.
Probably yes. So of course, microscopy is a field where we're very much prominent, and where such features are needed. But yeah.
There's a company in EPIC, in the network, that is actually developing a technology for skin analysis. The company is RiverD, and we have Gerwin Papas, the CEO and founder of RiverD International BV. Gerwin, good afternoon. So you are focusing on developing Raman technology to do in vivo skin analysis and also in vitro skin analysis. You have a little Raman probe. You could tell us a bit what you do, and then maybe you could think about what kind of low light cameras could help your business.
Yes, so what RiverD does is to develop and bring to market diagnostic applications of Raman spectroscopy. As you probably know, Raman spectroscopy is not blessed with very high signal levels. So that's also why I'm here, to hear the latest of what's going on in terms of cameras and camera systems that can deal with low light. So most of what we do is in the near infrared. I've heard that, I've seen that term come by a couple of times already. Actually, what you see here, what Jose is showing here is some of the, let's say, professional niche applications, so high-end systems, but we're moving more and more towards, I would not immediately say consumer level, but in the end is the goal. So my goal is to have a few of these applications actually in the end up in wearables and in mobile devices. So that means quite a few jumps for Raman spectroscopy. It also means that we cannot use, if I look at the cost drivers for Raman, then it's on the one hand, it's lasers. So we're trying to address that with the photonic integrated circuits. On the other hand, it is the camera systems that we're using. That's why I had hoped to hear a little bit more about the type of cameras that are being developed, for instance, for the automotive industry, which is also where cost is also, of course, of the essence. And I think for Raman spectroscopy, just imagine that you have this technique in your watch or in your mobile device. You just take a spectrum of something, it goes up in the cloud, and an answer comes back. I mean, I think there are thousands of applications that you could develop on this. So that's what we're sort of playing around. We have some ideas with it, and one of the things that is certainly essential is is that we come up with simple detector arrays, sensitive in the near infrared, but easily producible. So in high volume but low cost.
I'm gonna match this because first we are gonna talk to Leica, and after Leica, I want to have a bit of a discussion about your ideal detectors in terms of size, in terms of amount of pixels. But let's go to Leica first and see what they are doing because it's very relevant to this, and then let's have the discussion. We go to the key camera manufacturer, the main camera manufacturer, the most amazing camera manufacturer, Leica, Francisco, Antão. Thank you very much for being with us. The floor and the attention of everyone. If anybody hasn't seen the Leica Museum in Wetzlar, you have to see it. It's fascinating. The floor is yours, Francisco.
Thank you very much. I'll share my screen.
The Leica Museum in Wetzlar is really, truly fantastic. You can see the history of all the Leica cameras. We see it crystal clear, the way that it should be. The floor is yours.
Yeah, thank you very much. Thank you for having me. First of all, I would just like to introduce myself. I'm Francisco. I'm an optical designer here at Leica, Portugal. Today I'll bring you some discussions on future prospects that we have and what we're looking for in this topic. So first of all, I would like you to maybe understand our perspective at the moment, because we have so many worlds inside the Leica world, from microsystems to photography and sport optics. And today I'm actually going to focus on sport optics. So we're going to move from our specialty of cameras and to our newest one, where we're trying to be world leaders as well in sport optics. And what's the main differences between these two? Here we'll focus on precision mainly. That's our key focus, but we keep having the same characteristics from both industries. So we have precise manufacturability, but we also have, apart from our image quality that Leica has, we also have a greater production rate for spot optics, because it's something that it's produced more and more nowadays, with so much application, just from observation to hunting to golfing, and we are moving fast on this topic. So this is what we have for you, and what we look for here in sport optics focuses on low light, or I'll pick on the previous presentation because it's basically what we're looking for as well, which is this connection between low light and the detection of signals in high noise situations. So it's a little bit of a connection that we can make. It's not exactly a detection under low sources, but detecting our low source in a high source environment. And today, what we're really proud of our accomplishments so far. We have high range detections of over 3 kilometers at the moment. And we also have our accuracy and precision to a very, very low standard at the moment. And we would like to keep this as we go forward. So as you can see, we around our range, we can get mostly detections under 2 meters of accuracy, which is on these ranges, it's quite precise. But if you compare something like a huge mountain and a small tree, if somebody wants to detect trees at 3 kilometers range, then maybe a 2 meter accuracy is not exactly what the customer would want. So for the future, what we actually would like to improve is this precision at low range, and at the same time increase it as well. So mostly, if we can get over these 2 marks, it would be the goal of this meeting. So exactly, what are our challenges at the moment? We can connect, and that's that was my first point, between the low light theme of today and the low source intensity in environments with sun, nature, everything that's even during daylight, which is the most important focus at the moment for Leica. And this would mean detecting our laser pulses at long distances, even if they have a low intensity. And at the moment, the connection between the signal that we emit and the noise that we get is not the perfect connection for Leica. And this is precisely what we're looking for. I'm already pretty happy to hear the previous conversations, because especially with LiDAR, we've seen that there's this connection that we have between detecting between the empty road and our application. It's basically the same point that we have at the moment, and we wanted to know if there's new technologies apart from what we employ at the moment in our lasers and our detectors. So this harmony, we can improve one, improve another, maybe keep one of, and that's what we want to hear from you at the moment. So in the future, we're focusing on our signal to noise ratio, which with the sun playing a huge part can lead to a low detection, since we work on the infrared at the moment. And one of the few other alterations that we would want to do, or maybe if somebody has an application on this, would be to narrow our detection band to filter noises, maybe shorten our pulses, which at the moment are at the nanosecond range, and maybe also increase laser power, even if and trying to keep it at the class that we have, so the laser safety that we want to keep it as well. Even with that being said, with all these improvements, Leica is Leica, and so we would like to keep our standards for the future with sensitivity, with our great image and photography, and most importantly, our high transmission. Thank you very much.
Thank you very much, Francisco. It's very interesting, this a little switch of topics and applications, but at the same time, hearing that much, that there is so much overlay. So the technology is still pretty much the same, no matter what you are using it for. You mentioned also that it is for low or very noisy detection in very bright environment. So could you put maybe a bit of a numbers on it? So what do in your case, what is really the low lights versus the highlights?
Yeah, exactly. So low light means for our cases, it normally means that the pulses that we emit, imagine at the 3K range or the 3K kilometer limit that we have at the moment, for example, and at some other distances, if our target tends to be quite small, the pulse that we actually detect, even if we send a huge number of pulses, normally the accumulation that we get, it gets an intensity that's basically fits inside the environment noise. So normally, Leica works. We have solutions on our technology, but we also do some software filtering. But we would like to know if there's technology that could maybe detect our single pulses exactly at the range of noise of our light environment, typically, yeah.
Okay, so I would say it also sounds a little bit similar, or Gerwin, correct me if I'm really wrong, when we discuss the Raman imaging, because there is also a lot of noise coming around and you really need to pick it out. So I'm very curious if later in the discussion we will find out that there is a lot of similarities in the technology which needs to be used also between the live detection and here the detection of the distance and LiDAR. So it would be really interesting if there is this one golden bullet. Gerwin, what are your thoughts on it?
Yeah, well, that's so. What we're trying to do is move Raman spectroscopy out of the lab into, for instance, hospitals. So yes, for all kinds of applications development for Raman, you need the high quality instrumentation. What we're trying to do is to make the step that we, from those applications development, we define, okay, for this particular application, this dedicated application, we need as little as possible. So we're moving, I would say, more away from that. So trying to define, okay, what do you really need of a laser? What do you really need? What's the minimum requirement for a detector system that you can get away with? And of course, for Raman, that's always, you always need the sensitivity because there are not too many photons around. Noise does play a role, but we really don't need to go to the sub 1 electron readout noise because it's always determined by shot noise of the signal itself. But sensitivity, simple arrays, but especially the near infrared sensitivity, that's I would say almost at the top of the list. The second thing is that we would like to be able to use it at room temperature. So any way that minimizes dark current will also be important for us.
Okay, so we have Michael from Pi Imaging who has a question or perhaps even suggestion for you. Michael, would you like to unmute yourself and share your thoughts with us?
Yes, of course. Let me also include the video.
Fantastic.
I know that also while imaging Raman signals, you also have fluorescence superimposed. To mitigate this issue, people have used gating because, as we know, Raman is coming right after the pulse, so it's a very fast signal. But this depends, of course, on the application approach. It might not be an issue for Liver-D.
Oh, it is. Don't worry.
You have this
often enough. Yes.
Okay. So in that case, if the fluorescence noise is an issue, then I suggest to check out also time-gated Raman. And in that domain, of course, pads are a great tool to have because they can have a very fast gate response in the order of below one nanosecond, of course, with a rising edge of 100 to 200 picoseconds. Just a suggestion.
Yeah, well, I know it has been tried and shown to work. It depends, of course, a little bit on the source of the fluorescence because sometimes that can be pretty fast as well.
Yeah, of course, yeah.
And it tends to make systems more expensive because then you need the picosecond laser or something like that. But yeah, for some applications, it might actually be the solution.
Okay, and meantime, we also got a question from Sebastian from Hamamatsu. Also, would you like to unmute yourself?
Yes, yes, it goes basically into the same direction of the fluorescence background, and it was partly already answered by Jervin. He said that you're looking into near infrared sensitivity. Was that correct?
Yes.
So what is your typical operation spectrum, which would be, of course, important for the sensors?
Usually we detect signal now between 800 and 950 nanometers. But that's really determined by the sensitivity of the silicon-based detectors. Yes. So if I know that there are some developments to trying to push this a little bit further, any information you might have on this would be very welcome.
Not right off the bat. We might get in contact later on that regarding that.
Sure.
Yeah.
Perhaps fantastic. So even more discussions to have offline. But now I know that Jose really wants to get with his questions. I will be more gentle with my words now. Get with his questions to Francisco from Leica.
So this time gonna be provocative actually. So Francisco, we're very aware of the new line of products on Leica, which are the made in Portugal lenses. I would like to ask you about the need for coatings and thin films technology for these lenses, especially low light condition. Are you aware of some demands for different coatings for the optics?
Would actually need to discuss with some colleagues. My focus at the moment is on sport optics and range finding, but what I can say now is that The new objectives that are coming with special coatings made in Leica, and they typically detect the same light that our rangefinders do, and our rangefinders work with about 4 to 5 photon detection, and our cameras can do basically the same. And I honestly can't go much further than that because it's not my field. I'm sorry.
I am not. This is not a sales meeting, but I would like to congratulate Leica on this fantastic new line of products, especially for the price that these high-end lenses are being coming out. Really, quite a breakthrough. I think you deserve a prize for that, actually. So it's spectacular. But let's talk about the sports optics. So when it comes to sport optics, what are your items in your Santa Claus Christmas list for the optics part, not the detectors, but the optics? What kind of optics would you like to have that you don't have?
Okay, so for the optics, both in binoculars and compact rangefinders, we do have some limitations on. So the main goal is that on both these applications, we try to minimize everything. So that's one focus that we have at the moment, and our Christmas list for this year would be to get the same quality that we have now and keep on maybe shrinking and compacting our products. So we're talking about performing with the lenses that we have now and maybe reducing the size of it. That would be a great goal to achieve optically. But on the range finding specifically, we now have a challenge. I would say the biggest one, which is to filter the wavelength band that we now detect on our lasers, on our range finders. Typically we can filter in a 200 nanometer window, and we would like to maybe shorten that. Yeah, so that will lead us to maybe lowering the signal to noise ratio that we have at the moment.
We have in the room Christoph Boschart from the thin film company Kiehn. Christoph, good afternoon.
Good afternoon.
Here comes a challenge from Leica Portugal in sports optics, filters with 200 nanometer band. Francisco, would you maybe you could define more what is the starting and stopping wavelength of the filter?
Yeah, sure. So at the moment, our lasers work at the 905 nanometer, and we can do lower than 200 nanometers, but ideally we would like to focus on a 10 to 20 nanometer window around the 905. I'm not sure if that's a thing at the moment. That's what we're looking for.
Quite a challenge for us with wet coating. So probably would look more like sputtering coatings to reach these kind of filters. So that is something some other partners of us maybe can offer.
Okay.
We have many companies that are going to be able to contact you after this, Francisco. Be prepared. I would like to also bring to the room one person that we have in the camera business in Switzerland, Benjamin Gallinet from CSEM. Benjamin, good afternoon.
Good afternoon.
I don't know what you thought so far. We had just Leica presenting their line of sports optics, looking for partners. They're looking for a specific filter. We have had in the past many discussions about reducing the size of the optical instruments using micro optics and using actually nano optics and meta surfaces. Is there a room for cooperation there?
Well, we need to look at the details, but usually the devil lies in the details, right? But I mean, it's something we've been very active in miniaturizing the optics and the filtering technologies all around. And we've been developing very compact multispectral systems. Also, meta surfaces are something we are looking in actively at the moment. Micro optical arrays are for sure a solution in many different application fields. So yeah, I think it would be interesting to get into.
Francisco, actually CSEM is running the pilot line Fabulous, which has money from the European Commission to start pilot projects on the manufacturing of micro-optics enabled processes. So for them, the fact that you're looking for a potential R&D cooperation to bring meta surfaces or nano optics into the camera sector, into the sports optics sector is fantastic news. So I think there's going to be a follow-up meeting on this. I am sure, Benjamin, that we're making it happen. We'll bring Rolando Ferrini to the task, but this for me is a highlight of the meeting. We're going to be able to contact you later. I want to go now to Edlingen. Many people don't know what Edlingen is, but Edlingen is south of Karlsruhe. And in Edlingen, you have Fraunhofer IOSB. And that's the most important EPIC memories in developing low-light camera-enabled systems for defense and security. And Uwe Adomit, who have met many times in European Defense Agency-related events. Uwe, good afternoon.
Hello.
So what are in your challenges, in your systems, what are your demands, your items in your Santa Claus Christmas list for low light cameras? We discussed offline that there is a large amount of unmet needs. And after you, we're going to have Thales presenting. So just so you know, what are your demands?
Maybe a comment first. We don't develop devices, but we are interested in all kinds of night vision or low light devices. And for me, the demands are very simple. You have today the image intensifier. So when you want to replace it with a detector, you have to get at least the same performance as an image intensifier does. That means quite simple. You need a sensitivity as high as that of an image intensifier, and you can easily calculate that you need at least 4 megapixel detectors to replace the spatial resolution of an image intensifier. And when you get this all with the same power, weight, and size of an image intensifier, then you are there. So that's a quite high demand on a detector to replace an image intensifier for night vision applications.
I'm always honest. I'm not sure I got the challenge. Challenge in the amount of megapixels or in the noise floor of each pixel?
The demand is to get all together.
Okay.
So you have to get a high sensitivity of more or less single photon detection. You have to get the 4 megapixels at a frame rate of roughly 100 hertz. And you have all to do it on a, let's say, 6 to 8 centimeter in the cubic centimeters. So that's the task, and that's a very high demand.
Whenever I had a task or a challenge on detector, I go always to Jan Vermeeren, always go to him. And then I ask him to please translate. So the challenge is, I think 4 megapixels SPATs is not in the state of the art, or is it? And if not, what is the closest we can get?
With SPATs, we are certainly not there. On the other hand, I was also thinking you have also electron bombarded CCD or electron bombarded CMOS image sensors. Can they not replace image intensifiers? Because ultimately at that moment you have a much more compact solution than using an image intensifier.
No, I disagree. I'm sorry.
Yeah, fine. But give your argument, please.
Because, as I said, it sounds simple because 4 megapixel doesn't sound much when you look what's available in the detector market. The problem is, first, when you stay with electron bombarded, you still have the photocathode of the image intensifier. That's a drawback to some of the applications. The second thing is, even for electron bombarded, you are far away from the 4 megapixels. The most you get is roughly 1 megapixel, up to 1600 by 1300 or something like this. And what's also often overlooked is you need, as I said, this on a very small scale, and you need a display of the same size. And when you look, all components look simple, but when you want to put it all together, you have a very high demand. That's what's typically overlooked.
I mean, in general,
yes,
as I've shown you earlier, the Orca Quest, except for the size constraints, matches all the demands. But I guess it's a very different application there. So I mean, just like the demands can be combined with a couple of different drawbacks there at the end.
Yes, because the the problem is not to get a single component doing what it should, but the problem is really to combine everything on a very small scale.
But normally an image intensified, let's say, camera is to a certain extent pretty bulky, because you have, let's say, the image intensifier in front of a, say, a regular CMOS image sensor. And let's say you have also to be careful quite often with most of the image intensifiers, that if you have, let's say, at a certain point, a little bit of over illumination, that you get completely blinded.
You have a lot of advantages when you switch from an image intensifier to a detector mosaic, at least in theory. The problem is that currently, at least in my opinion, there is no technology available to do it on the same, to replace the image intensifier on the same scale.
I'm going to ask Photonics, because we had them in the room and I have discussing online the image intensifier tube. Benjamin, Fradin de la Renaudier. Benjamin, good afternoon. You have heard the discussion. We have a challenge with the image intensifier matching to the CMOS. Could you tell us about how you target this, and perhaps there is some room for cooperation here in a project, beautiful project between Caleste, you, and Fraunhofer IOSB? Hello. Tell us about this. Benjamin, I think we lost connection with Benjamin. And Detra, Benjamin?
I guess he is muted.
Sound, we're going to go to Thales now. We have four fantastic speakers today. We started Valeo, Ibeo, and then we had Leica, which stole the meeting, and then afterwards we finished with Thales, the key company in the defense security sector and aerospace sector in Europe. Thales is represented today by Eric Belhaire. It is fantastic to have you with us. You saw what amazing discussions we've been having. Send us off the way that we deserve. After your presentation, we have another round of discussions on how we can make Thales even greater than already is. The floor is yours, Eric.
Okay, I'm trying to share my slides. I hope it's okay for you. So Thales, as you mentioned, we are making mainly defense equipment, even if we have some other activities in the civilian domain, like in lasers and other type of technologies. But today I will concentrate on what we are doing in the defense applications. For us, low light level is seeing by night mainly. Here I put the level of night that we can have, and what we want to have is to provide to mainly the soldiers a way to see by these overcast starlight. As I heard the discussion with Uwe before, and mainly I think that he mainly knows this kind of subject. It's really important to see that it's really in this type of level of night that we have the most challenge. In terms of, let's say, okay, here in terms of products, we are doing products to see by night for more than 25 years. And so we have a quite long experience. And here you see a small view of the different products that we have built in the time, from all those equipments are using I-square tubes, I-square tubes that have been mentioned before in the discussion. Here you can see some products which were using a single tube and which were having a single ocular, and we can have some others product like this one. We can have a single tube and two oculars, and we can have at the end some double tube equipment in order to provide a better vision to the soldier mainly. And so if we make a short summary of the different types of products that we have some products which are dedicated to airborne, which are the most challenging one. I will explain a little bit later why these one are more challenging. And we have some products for soldiers, which could be yes, very small in order to allow let's say easy transportation by the soldier, which could be more technical. And we could provide on the last product, you would find something which would try to provide some augmented night vision to the people who are using these equipment. And augmented means that you can make superimposition of some other symbols on the I-square tube image, and this is possible, and I will show you before. Why is this more challenging for airborne? It's mainly because in airborne, the man who will wear these goggles will use it inside the helicopter or inside a plane, where there will all this lighting of the dashboard, and you want to avoid all this lightning coming from the dashboard in order to not saturate the vision. And so it means that you will work only on the near infrared for this type of applications. You will not have any vision in the visible in the air, so which is not the case for this one, where you can have both the near infrared and the visible. And why working with the near infrared is because these equipment are also used to see some pointers, laser pointers, which are working at, let's say, 0.8 to 0.9 micron, which are outside what is visible by the eye of the people in front of you, what we call usually enemies. And so if we go to this last generation, what we call a fused image of a ocular, for example, here, if we just look what is visible by the I-square tube, you would find an image like this one. And here, for example, you don't see somebody who is in the middle of these trees. But if you make the superimposition of some infrared with this image intensifier, the intensified image, you can make the contours of somebody inside these trees appearing. This is very important. And so the fusion of infrared with I-square tube, which is one of the last generations which has been developed, is important to provide some new features to the user of this kind of night vision goggles. And so what is the future for this? We mentioned, and we had this long discussion concerning I-square tube. Why is it I-square tube used and not replaced by anything else? The future, obviously, we need to go to digital cameras. Currently, those cameras with I-square tube are purely analog, mainly. We have an analog image at the input, and you have a screen, which is a phosphorus screen that the soldier is looking at, which is purely analog. But if we go to go further, we need to move to digital. I've shown you some cameras which are going in this direction by including another screen to make the fusion between the screen of the phosphorus of the I-square tube and the screen outside in order to superimpose some information. But this is very important to share the image in a situation also. If we want to transmit the image of the I-square tube to somebody else in the environment, we need to go to connected cameras. We need to go for that to the digitalization of the image from the tube or coming from the scene. And so we need also to register usually the intervention for proof or some legal aspects. And we need to implement augmented reality. It can help for navigation or geolocalization, to provide some alerts, also to give some information of who is the friends and foe, so to avoid anti-fratricide damage. And also, we can add some processing which could help to have some target identification with some AI, for example, and to implement some improvement with image processing. But all this needs to be done at a very low power consumption. And that's why we find again and again, and we will find maybe for some years, some I-square tube on the field, is because the power consumption of I-square tubes is very, very low and very difficult to attain with any other technology. We speak about something which is in the range of 100 milliwatts. And why do we need these 100 milliwatts for a soldier? Is because a soldier needs to go in the field with a very small weight. The lighter is, the best it is, and to be lighter for let's say 2 days, he needs to go with very small batteries, and these very small batteries need to last for a very long time, and so we need to be at very low power. We cannot afford to have, let's say, a 10 watts power consumption. For example, it's far too much, and it's not possible. So the requirement for the future would be to be at around a night level 5 that I introduced before, which is an overcast starlight. As had been mentioned by Uwe from Fraunhofer, it's around 4 megapixels that we need. It's not really 4 megapixels if we are at a deep night level like level 5, because in that case the resolution is a bit lower, but for night level, let's say between 1 and 3, we will need to have this 4 megapixel resolution, obviously, and the frame rate needs to be quite high for mobility. So it has been mentioned 100 hertz. It could be 60 hertz if it's not a fast moving soldier. The latency is also a key parameter. You cannot have to a large latency between the image and what is presented to the user, especially if in case of mobility. And the power consumption needs to be in the range of a few hundred milliwatts, so it's very difficult. Obviously, we don't want to have any export control, and the weight needs to be in the range of a few hundred grams, not more than that. Otherwise, it's very difficult to wear it on the head of the soldier. And so there is several possible candidates for in terms of technology. We spoke about SWIR during this meeting. SWIR is very interesting. SWIR is very interesting because during night, we have this night glow, which is always present on Earth. For example, if this night glow is in the SWIR region between, let's say, 1.4 to 1.8 roughly, but you have this, which is the different curves here are showing what is the radiance for different type of moon, from full moon to new moon. And when you go from full moon to no moon, you see that in the visible, there is a large variations of the radiance on Earth, which is not the case in the SWIR. In the SWIR, you will maintain something which is very constant. So it's very interesting to go to there to say, oh, even if we have no moon, we could have a lot of photons in there. But the problem is that even if we have a lot of photons, we need a very low noise SWIR sensors for that, which are not available now. We need to find some SWIR sensors with, if we keep the quantum efficiency constant of what it is now, in the range of less than 10 electrons of noise. So it's very, very low noise in comparison to what is available on the market right now. It could be another candidate for the technology, could be some CMOS, which is very interesting. CMOS is improving daily. It has been mentioned by Amamatsu, some detectors, some CMOS detectors with 0.3 electron of noise. 0.3 electrons of noise is becoming very interesting. With this kind of sensor, you can count every photon, roughly. And this could bring you very interesting technology, but the problem is the power consumption as usual. And another option would be to move to take only a standard CMOS low noise, maybe not 0.3 electron of noise, maybe a little bit more, with an uncooled infrared, which would allow the use by day also. The problem, another problem of I-square tube is that you cannot use them during day because they saturate. So this is really interesting to have this. And so thank you for your attention. I just wanted to point out these possible future technologies.
Thank you very much, Eric. And it's really great to have this slide here. So you have quite a list of different requirements to the sensors and even a little bit of solutions possible. So I think we can have a nice discussion here. And I see that Jan being quite eager already to get into discussions. There are so many questions popping up. So Jan, I would like to give you the floor to ask your questions and come up with your comments. And maybe you could start with the very last statement that Eric did about the 0.3 electron of noise for CMOS. Is it something what Kailesta also can do, or what do you have to also add on that?
1 to 3 noise electrons in CMOS image sensors is certainly possible. Also taking into account that you can have a very high quantum efficiency, and that it's possible to tailor the peak quantum efficiency a little bit more to the red tag, for example, what is at this moment done with conventional commercial image sensors. I agree with Eric that, let's say, for the shortwave infrared, reaching 10 noise electrons is challenging at this moment, even when you go to smaller arrays and integrated arrays, like, for example, what Sony is bringing on the market, it's remaining difficult. On the other hand, what I'm seeing here is that, let's say, certainly when you talk about compact solutions, and that's also what your colleague of IOSB was referring to, you're, let's say, going then for, let's say, image intensifier solution, which is end-to-end analog, so to speak, where you, let's say, don't have electronics in the loop, and you can also not have, let's say, a centralized command looking to the image intensified images. In case you go to such type of a solution, you need to have an, let's say, CMOS image sensor somewhere in the loop. And yeah, unfortunately, and most probably difficult to avoid, if you want to reach, say, 50 or 100 hertz frame rate at 4 megapixel, your power dissipation will go up. If it will really reach, let's say, 10 watts, I doubt a little bit, but it will be certainly more than, let's say, the 100 milliwatts, which you, let's say, considered for the pure image intensifier tool. But I want to do, as I said, either, let's say, C4 operations, or you want to go for image fusion. I guess you have to accept such type, or let's say, slightly higher power dissipation, unfortunately. And let's say my typical question was, you request here almost 100 hertz frame rate. On the other hand, I doubt a little bit if the phosphorus, which are used at this moment for at the viewing side, are that fast. It should translate into a decay time of approximately 5 milliseconds, where I presume that most of the phosphors are more optimized to have, let's say, kind of integration by the eye and integration into the phosphor.
In fact, you know, it's a little bit less than 5 milliseconds from our experience, and more importantly, the latency is very low. And so this is very important when you have these mobility requirements. When you move the head, for example, the image is directly following it, and it's easier if you want to pilot an helicopter or things like that. It's very important to have this very low latency, which will not be so easy if you go to digital vision. Because you will have some processing, which takes time, and so it's not so easy to maintain. And concerning the, in fact, yes, I already mentioned, but the time constant is lower than 5 milliseconds. Mainly, it's we have this. You know, you have this this integration made by the eye, which is in the range of 5 milliseconds, but the tube itself is faster than that. So that's And so I don't know if, obviously you had a question, I think, concerning the night glow also. It seems that you asking Jan in
yeah, the night
in
indeed.
the chat.
If you go for a very, let's say, dense cloud cover, I doubt a little bit if you can still benefit from the night glow. In an open sky, and that's what, let's say, the curve which you are showing is known for. That's an open sky with different moon conditions.
Yeah, it's true that we have a decrease of the when in the case of overcast, and we had also some question concerning if it's maintained during the night, because we know that the origin of this night glow is coming from the sun by day, and in fact what has been observed is that during the night you have an evolution of the level of the night glow by, if I remember correctly, a factor of 2 to 3, and if we had some clouds, EV clouds, it's decreased also, but as the clouds are re-emitting a lot of photons, it's not suppressing completely the night glow. So maybe we would need to have some vision in deep overcast sky to have even higher noise requirement for the SWIR detector, maybe at 2 electrons, 3 electrons, or whatever. But we still have this phenomena. This is always interesting to have it during the night. We do not have the technology to benefit completely from it, but maybe in the future, if some progress are done by the industry, we would be able to benefit from that.
Mm.
Okay, that sounds like a great discussion. Maybe you should also connect for more discussion offline. We still have a few questions and few comments coming up, but I also would want to bring a little bit of attention to Martin Parker from Thor Labs, who are developing a lot of different components for multiple applications. Martin, would you like to unmute yourself and tell us a few words about Thor Labs and low light imagers and sensors?
Yes, and thank you everyone for giving me a couple of minutes to talk about our capabilities. I'm Martin Parker. I'm the Director of Engineering at Thor Labs Scientific Imaging. Thor Labs is obviously well known in the photonics field, but not necessarily common knowledge that we design and manufacture cameras. And so I just wanted to talk quickly about our capability. Sorry, I'm not super familiar with Zoom, so you'll have to just give me 1 second to.
If you just look at the bottom of the screen, the green button, that should be relatively easy.
Okay, hold on.
You go to the bottom of the screen, you click share screen, and then very important, you select the screen you want to share with the universe. Yes, fantastic.
And we already see it.
Okay. All right, sorry about that. Yeah, so just a very quick introduction to our cameras and capabilities. We have a variety of cooled camera products, standard SCMOS and cooled CMOS cameras. Among other things, they feature low read noise, trigger latency, and jitter. Our cooled cameras utilize either BAE SCMOS devices or Sony IMX series CMOS devices. We have hermetic cooling chambers with metal seals, so you get a long life, maintenance-free. And we also eliminate the fan in our cooled cameras because it's kind of a primary thing that we want to eliminate the vibration that can cause motion blur and also the maintenance issues with fans. Of course, we have compatibility with all of our photonics tools, Thor Labs photonic tools. So we can interface to cages, tubes, post components, etc. And we can also accommodate 25mm filters in windows. And then from a software perspective, we have a rich set of interfaces for software for connectivity, both in Windows and Linux. And just a quick discussion about our company capabilities. I mean, as it relates to cameras specifically, We have offices in Germany where actually several offices where a lot of manufacturing is done, France and the UK, and of course headquarters in the US. Our cameras are designed here in Austin, Texas, in the States. We have laser welded hermetic chamber capability, thermoelectric cooling capability. In fact, right now we're in the process of developing a deep cooler for a certain type of detector. I can't really talk a lot about it. We can also remove sensor cover glass. So that's a very tricky and kind of excruciating process to remove the cover glass for applications where interference effects of that cover glass might be detrimental, particularly in coherent light applications. Of course, you probably know we have a large catalog of over 20,000 photonics components and instruments, and we're also really vertically integrated. We manufacture much of what we design, of course, including cameras. And so that allows us really to provide custom solutions, not just cameras, but optics, coatings, mechanics, even at a system level. And here are a couple of examples here. This is for an electron backscattering application, and this is for a Raman spectrometer. And this is a camera manufacturing facility in Austin. And finally, we have an OEM solutions group that really facilitates a relationship between Thorlabs and OEMs for those who might want to integrate our product, even at a system level, into their own. And that's a relatively new development. So yeah, I just wanted to let people know this is really the first such presentation I've been to. I really appreciate the opportunity. And also, if you think that you have some technology that might be relevant to us, particularly in cameras, but anywhere, we'd be very, very happy to talk to you. I tend to do the characterization of new sensors for various applications.
Thank you very much, Martin. And you are right. Many people don't know that Thorlabs is a manufacturing company, and especially in the field of cameras, they do this fantastic work. We are looking forward to have you, Martin, more often at our meeting next time with a featured presentation with your unmet needs and challenges for the rest of the community. But before we close the meeting, there are two people who I want the closing remark from. First, I want to go to the ST Microelectronics, Eric Masalera. Thank you very much for joining this meeting. What's on your mind?
Yes, I have last question maybe for Eric Belhaire regarding shortwave infrared requirements. Is it still time to ask the question?
Yes.
Okay, so my question is related to, so I understood Eric is looking for fusion between shortwave infrared and digital visible camera. So the question is, what would be your requirement regarding the resolution of the shortwave infrared camera? Would it be 8 megapixel or?
I think that, yeah, for the shortwave infrared, if you want to address deep night and have no other sensor, it would require to have, let's say, roughly 3 million pixels, maybe, or something like that. So it's a lot. But if we try to make the fusion with some visible camera, which has a higher resolution, maybe we can decrease a little bit the resolution of the shortwave infrared. It depends really on the architecture that we are choosing. For this, to make this choice, we will need to make a lot of experiments. And it will depend also on the noise level, and the quantum efficiency of the technologies that you can propose. In fact, Eric.
And the final question of this meeting goes all the way to Edlingen, goes to Uwe Ademait. Uwe, the closing remark. What's on your mind?
I have only a comment to the shortwave infrared also, because the problem is a little bit that it looks very good from the spectrum point of view, but unfortunately the shortwave is affected a lot by the environmental conditions, and so you have a very high variability, and it's, at least in my point of view, not fully clear if it's really very good replacement. It has its advantages, definitely, but it also has some drawbacks, and a lot of more information on the illumination levels created by the radiation is necessary, in my opinion. And also,
yes, please.
Yeah,
sorry,
I share the same conclusion. In fact, you know, I know that there were some campaigns in order to make some measurements around the globe, because it's not to be done only in a single city, but it has to be done everywhere. And I'm sure that in fact we need to increase this level of knowledge concerning that.
Yes.
Uwe just opened the Pandora box with that demand for shortwave infrared. Allow me to summarize quickly the meeting. We brought use case in medical, defense, automotive, and sports optics, and we wanted to match them with the technologies of the key companies in EPIC developing low light cameras and detectors. And I think we did a pretty good job. Fraunhofer IOSB and Thales are interested in 4 megapixel or almost single photon plus image intensifier. Thales also looks for a partner on fusion of digital camera for shortwave infrared. Automotive was addressed by Ibeo and Valeo, and they were looking for ways to reduce the size of SPAD cameras. Sports optic was addressed by Leica, and they are looking for potential collaboration to reduce the size of the full optical element. Meta lenses were proposed to them. And in the in vivo imaging, River D wants to bring the Raman spectrometer solution for skin diagnosis to the consumer market, and they have a challenge with the size and the cost of the detectors. And for me, I really love this meeting. I think there is a lot of room for cooperation here. Let's now close the meeting, and you can stay afterwards for a nice drink. And that concludes the public part of today's meeting. If you are in our Zoom room, our informal private discussion is about to start. I call it virtual drinks with friends. And we all know follow-up is important. But for now, if you are watching on YouTube, that's where we leave you for today. Thanks to the EPIC production crew and our sponsors for making today's event possible. More details about upcoming meetings are on our website, and if you want to get